Okay, so let's move on and talk about nomenclature and naming chemical compounds. So we're moving away from the historical aspects, and predicting trends off of the periodic table. So now let's think about naming. I've already introduced two classes of types of compounds, ionic versus molecular. And so that's very important when it comes to naming, because each of those different substances has different rules when it comes to naming. So the first step into naming a compound is to identify, is it molecular or is it ionic? So we're moving kind of into the symbolic domain of our atoms, molecules, and ions discussion within this chapter. All right, so let's review the types of compounds that we've addressed so far. We have the ionics and we have the molecular compounds. Since we just left off on predicting charges of ions, let's talk about ionic compounds. So remember, the main thing to identify an ionic compound, its identifier is it's composed of a metal and typically a nonmetal or polyatomic anion or something. So we have a metal cation and a non-metal anion. And so if you remember our periodic table, metals are on this side of the periodic table, all right, near lithium, sodium, those are alkali and alkaline earth metals, and then our nonmetals are over on this side of the periodic table. So we have a combination of those two ions. And so we call them ionic compounds because they're defined by possessing an ionic bond. It's essentially the forces that hold the substance together. And we'll talk about ionic bonds, but an ionic bond is simply the transfer of electrons to form ions. And this contrasts to molecular compounds that we'll talk about. And again, our identifier for an ionic compound is that it's composed of a cation and an anion. The cation is typically a metal, where the anion, or the negatively charged ion, is typically a nonmetal. All right? And so in an ionic compound, the charges will always cancel. The positive charge will cancel with the negative charge and produce a neutral ionic compound. So, for example, if we have a metal A plus a nonmetal B, both of these are neutral in their neutral state. If they become ions, we have our A cation and our B anion with a +1 and a -1 charge. But then together, when it forms an ionic compound through an ionic bond, it produces an AB ionic compound where the charges cancel. +1 -1 equals an overall net charge of 0. Net charge of 0. So an example of something that would take on an ionic compound form would be like salt, table salt. Salt is sodium chloride. So we have, a sodium atom, a chlorine atom in their neutral state. There's a transfer of electrons that occurs where sodium will lose an electron to produce sodium plus cation. And then chlorine will gain an electron to produce a chloride anion. And you can see how those charges work out. We have a plus and we have a minus. So if those two ions come together, they cancel out their charge to give you sodium chloride, that's salt. And typically we call ionic compounds salts. So not just sodium chloride, like sodium bromide, calcium chloride. Oftentimes we just generically call ionic compounds salts. Okay, so that's ionic compounds. In your mind, you need to ingrain in your mind that the identifier is a metal plus a nonmetal in its chemical formula. All right, so let's talk about molecular compounds. So if we're still thinking about identifiers here, molecular compounds are always composed. Oh, I already have it there. I'm composed of nonmetals. Nonmetals. So all of the atoms, the elements within that chemical formula will be nonmetals over on this side of the periodic table. Okay. And so molecular compounds have a different bonding structure. The forces that hold the atoms together are a little bit different. They're defined by covalent bonds. These bonds and forces are different than ionic bonds. So in ionic bonds, it was a transfer of electrons to form those ions, but in covalent bonds, those forces holding those atoms together are through sharing of electrons. And again, molecular compounds are composed of all nonmetals. And so an example would be like methane, which has the chemical formula CH4. All right. And so you see carbon, hydrogen, both of those are nonmetals. So that would classify it as a molecular compound. Okay, so let's take a little closer look at the bonding description between ionic versus covalent, what separates an ionic compound from a molecular compound. So our first example here, so ionic's up top here, and we have a covalent molecular compound on the bottom. Let's look at ionic first. Ionic, remember, is the transfer. Those bonds are dictated through the transfer of electrons, while covalent is the sharing of electrons. So I'll show you what that means. So in this picture, I have salt. So we're looking at salt again, sodium chloride. So in this first picture, I'm just showing the outer shell electrons, which we'll get to in a later chapter. But essentially, this purple atom here, this is a neutral sodium atom. It's a sodium atom with 11 protons. Maybe I'll just write it. Yeah, 11 protons and 11 electrons. It's neutral. All right, and then we also have a neutral chlorine atom. So chlorine is neutral, and it has 17 protons and 17 electrons. So both of these atoms are in their neutral state. But we talk about ionic compounds and forming ionic bonds through the transfer of electrons. Sodium is a metal because of where it is on the periodic table. Chlorine is a nonmetal. And remember about our chemical properties of metals and nonmetals. Metals tend to lose electrons, while nonmetals tend to gain electrons. So when we put a metal and a nonmetal together, that transfer is enhanced because we have a metal that tends to lose electrons, and then we have something else, a nonmetal, that tends to want to gain an electron. And so that's what happens. So sodium will actually lose one of its electrons, and chlorine will gain that electron. And then what happens in the end is now, since sodium lost an electron, we end up with a sodium cation, or 11 protons, 10 electrons in its nucleus, and then a chloride anion, or negatively charged ion, where chloride has 17 protons and 18 electrons. And then the reason this phenomena is favored is because we now have noble gas configurations in both sodium and chlorine. So sodium here, if it loses an electron, it has the same number of electrons as neon. So sodium plus is very stable. A sodium plus cation is very stable. And then our chlorine here gains an electron. It gains the electron that sodium lost, and now it has 18 electrons, just like argon. So now we have two substances that have noble gas configurations, or the same number of electrons as noble gases, and that is very stable. So that's why, when we see table salt, sodium chloride, understand that written this way, sodium chloride, this ionic compound, is composed of a cation and an anion, sodium cation and chloride anion, to form that ionic compound. This does not exist, this substance doesn't exist as sodium and chlorine in its neutral state. It's actually as a cation and anion because it's more favorable for that electron transfer to occur. And then it exists in this ionic state. All right, so that is ionic bonding. But just remember, ionic bonds are made of a metal and a nonmetal because metals tend to lose electrons to form cations. And, we have the receivers on the other side. Nonmetals tend to gain electrons to form anions. And that's why we form ionic compounds. Oh, and I didn't even point out here. So, I talked about the force holding the substances together is an ionic bond, and what that force really is is we essentially now, once we have that transfer of electrons, we have this positively charged particle and a negatively charged particle. And so those charges will attract one another. So the charges attract. And that is what keeps the substance together. And what we call that is electrostatic interactions. Electrostatic interactions. So electrostatic just means charges. So we have, opposite charges coming together and being attracted to one another, directions. So that is the force that I'm talking about that's holding it together. Okay, so not only are the cation and anion stable because they're in a noble gas configuration, but they also form and stay together because of those electrostatic interactions holding that ionic bond together. All right, so that is an ionic bond between a metal and a nonmetal. Now, what about covalent bonds? Those are sharing of electrons between all nonmetals. So water here is an example of a molecular compound because hydrogen and oxygen are both nonmetals. So since this compound is completely composed of nonmetals, it is a molecular compound that's held together by covalent bonding. We said covalent bonding is formed from the sharing of electrons. So let's see what that means. So water is composed of 2 hydrogens and an oxygen. So I just have all of those neutral atoms here. I have a neutral hydrogen with 1 proton, 1 electron. I have 2 of them. And then I have an oxygen, a neutral oxygen. So all of these are neutral. So this oxygen has 8 electrons and 8 protons. Yeah. Okay. So they're all in their neutral state. So what sharing of electrons means is instead of, just hydrogen willingly giving up one of its electrons, what happens is that those 2 adjacent atoms will actually share their electrons with one another. Same here. So you see how there's essentially like both pairs or both of these atoms have just 1 lone electron. So if they both share their 2 like lone electrons with one another, then both of them will have a pair that they can share. And that pair of electrons is a covalent bond. So that's what you see here. So now we have a pair of electrons, and that creates our covalent bond. So that's what we mean by sharing of electrons. So both atoms will equally contribute 1 electron to produce that covalent bond. While over here, chlorine essentially stole that that extra sodium electron. So when we look at the picture of the actual compound, chlorine has all of the electrons, while sodium doesn't. While in our covalent bonding picture for molecular compounds, each atom shares equally those electrons that form the covalent bond. So we can draw similar pictures for molecular compounds such as methane or carbon dioxide, and we'll get more into that when we look at Lewis structures at a later chapter. All right, but that's the gist of it. Ionic compounds, those bonds, the ionic bonds, are formed through the transfer of electrons from a metal to a nonmetal to form your cation and anion, and then covalent bonds or covalent compounds or molecular compounds formed from the sharing of electrons in all nonmetal composed compounds. Okay, so let's take a deeper look at ionic compounds and kind of just review everything we just said and then talk about naming ionic compounds. So we're talking about ionic compounds, metal and nonmetal. So we already said ionic compounds that we oftentimes will call salts are composed of oppositely charged ions held together by electrostatic interactions. Electrostatic interactions. What we mean by that is the cation is attracted to the anion because they are oppositely charged. Cation, anion. Other things about how those cations and anions combine, they have to combine in such a way where the resulting ionic compound has no net overall charge. So we'll do a little practice in the next slide where we try to achieve that no overall charge in the formula. What I mean, how those cations and anions combine. All right, so some other things about ionic compounds. The unit that you actually write in the formula of that ionic compound, we oftentimes will call the formula unit. The reason we call it this, so if I write out NaCl, I can't just pick up one NaCl molecule because how ionic compounds exist, they exist as a network of sodium cations and chlorine or chloride anions, kind of like in this picture here. So the table salt that you have in your kitchen is actually composed of this crystalline structure, especially like a bunch of ping pong balls sandwiched together in an array where we get alternating sodium and chloride atoms with one another. So when we talk about sodium chloride, we write it in a way where we only are looking at one of the units, the ratio of sodium atoms to chlorine atoms in the whole network. So how this picture is depicted, this might actually be like, 20 sodium atoms and 20 chlorine atoms. But we don't want to write it that way as chemists. We want something that's uniform and consistent to convey sodium chloride to one another. So we take the use of the empirical formula. We want to simplify it in such a way where we just convey the ratio of sodium to chlorine atoms. So the simplest way to refer to sodium chloride would be just NaCl. There is one sodium atom for every one chlorine atom. Right? But understand in ionic compounds that those ions actually exist in a crystalline array. That there's no discrete molecule of sodium chloride. We usually just talk about them in terms of formula units. But oftentimes, sometimes I'll say like sodium chloride molecule. So that's actually wrong if I say it that way. So you should yell at me if I ever say that. All right. And then again, with ionic compounds, it's usually the combination of a metal and a nonmetal as our anion, metal as our cation. That's our identifier because that will produce ions. Ionic compounds are typically crystalline solids at room temperature. That's why we call them salts, because they will look like salt. Maybe not necessarily made of sodium chloride, but we call them salts nonetheless because they look like them. And then lastly here, the subscripts will tell you, the subscript to the right of each of the elements tells you what ratio that salt, that ionic compound is in. So for example, a different type of ionic compound like calcium chloride. So calcium chloride actually has 2 chlorine atoms for every, or chloride anions for every 1 calcium cation. So the subscripts tell you the ratio of ions in one formula unit. So the molecular structure, or the atomic structure of calcium chloride will look actually much different than our sodium chloride example here, because there are 2 anions for every 1 cation. Okay, so let's work on actually writing out neutral ionic compounds, how to get to that. So a main point in writing an ionic compound is to write it in a way where the cations and anions are in a ratio that's neutral. So we need to make sure that when we write that ionic compound, it's neutral as written. So we need to, one, know the charges of our cations and anions. But thankfully, everybody has a cheat sheet and can figure out what the charges of the majority of the cations and anions are. So for example, so what do I mean by neutral? Essentially, it means that the total number of charges that comes from the cations has to equal the total number of charges that comes from the anions. So we have to, one, predict the charge of the different elements involved in the compound, and then we have to take note of how many of each atom there is. So for example, here in our calcium chloride, note the subscripts. There are 2 chlorine or chlorides we have to account for when calculating our net neutral charge. So I think it's best to just practice it. So what is the compound that's formed between magnesium 2+ and fluoride minus? All right, so magnesium 2 plus, that's our cation. Fluoride is our anion. So again, we want those charges to cancel. So in my mind, if I put two fluorides together, overall there will be a -2 charge, and then that will cancel out the +2 charge coming from magnesium if there are two fluorides. So if that means if we have to have two fluorides, oh, I guess I was writing it there. So if we have two fluorides, an overall 2 negative charge and a 2 positive charge, that will make it neutral. The molecular formula, or sorry, the formula unit for this ionic compound will be magnesium fluoride, 2 of them, MgF2. Okay, so let's look at the next one. So we have what ionic compound is formed when we put together a barium 2 plus and a carbonate 2 minus, those two types of ions. Again, let's just inspect the charges. We have a 2 plus cation and a 2 minus anion. So in my mind, those two charges cancel out. 2 plus, 2 minus, boom, that's 0. So we don't have to put multiple cations or anions in it. We can just do a 1-to-1 ratio, and those charges will cancel out. So when these two ions come together, it's going to form the compound barium carbonate because of how the charges have to cancel. Okay, lastly, we have two different cations. So this is our one polyatomic cation that I want you to remember. This is ammonium. So it's not a metal, so this is one of our exceptions, but it's a polyatomic cation. And I give you the charge right here, so it's +1. And then we have a phosphate anion, which is 3 minus. All right, so in my mind, okay, we have a 3 minus and a +1. So in order to overcome all of that negative charge, I want actually 3 of these ammonias in order to cancel that out. So if you kind of think about it as just a summation of all of the particles that are present, the ions that are present. So if we have 3 cations that are +1, so that would be an overall charge of +3. And if we have 1 phosphate that is -3, you see how those charges cancel to give you 0. So this is the formula we would have to write. We would have to write this formula unit in such a way that conveys that there are 3 ammoniums. So I'm going to write NH4, but we want 3 of them. So I'm going to put that in parentheses. And then we have 1 phosphate anion. So there is the answer for making a neutral ionic compound from ammonium and phosphate. So now that we can identify ionic compounds and piece together how ionic compounds come together from their respective cations and anions, now let's talk about naming. So these rules only apply to ionic compounds. So the main rule for naming ionic compounds is to first name the cation, then name the anion. With the anion, you need to use a special suffix. And the important thing to note here for ionic compounds only is you never denote the number of cations or anions in the substance, because for most of the cations and anions, we can predict the charges from it. And so those charges is what determines the subscripts and the number of anions and the number of cations that produce a neutral substance. So there's no need to denote in the name how many cations or anions there are. And then also, there are special rules for transition metal cations, but for the most part, you always name the cation, then the anion. And that's the same thing for writing out the formula unit. Whenever you write it out in the chemical formula, you always write the cation, then the anion. So here's a couple examples. So this first example here, we have magnesium and fluorine, and you see that there's 2 of them here. I think these were the examples we had up on the previous slide. So how we would name these is you first name the cation, which is magnesium, and then you name the anion, but we need a special suffix here. So fluorine, so this is a fluorine atom off of the periodic table, but because it's the anion, we need to put a special suffix. So we change the "ene" into an "ide" because it's an anion. So this becomes magnesium fluoride. All right, so that's the first example. So the second example here, we have barium carbonate, and so that's the name of it. So we name the cation first, so it's barium, and then the anion. So if you look at your polyatomic anion sheet, CO3 2 minus is carbonate. So it's just carbonate. That's the name of the anion. So that's barium carbonate. And then lastly, this one. So both of these cation and this anion are polyatomics on our list. So NH4 minus or NH4 plus is ammonium, just on our list, and then our PO4 3 minus, this is phosphate. So it's just ammonium phosphate. And again, see how I did not denote, and I didn't say, tri-ammonium or ammonium 3. I didn't denote how many ammoniums there are because ammonium always has a set charge that you should know. Um, so this name is just ammonium phosphate with no indication of how many of those cations or anions that there are, because you can figure that out from the name and the predicted charges to get back to the chemical formula. So those are just some examples. So let's go into more detail of naming ionic compounds. So let's look at the cations first. So the criteria for naming cations, if it's a monoatomic cation, um, it's quite easy to name the cation if it's monoatomic, meaning if it's just one element off of the periodic table, because it's just the name of it. Sodium cation is just sodium. Calcium cation is just calcium. And so remember, with cation naming, typically the cation is a metal. So in at least two of these examples, magnesium and barium are both metals, right? And so the cation name is the same as the element name, only for monoatomics. It's different if it's polyatomic because that has its own given name. And then if it's the stocks, if it's a transition metal, you need to use the stock system, which we talked a lecture back about the stock system to indicate the charge. So you need to indicate the charge. So see how in monoatomic cations, anything that's off of the periodic table within our main groups, these metals you can easily predict the charge just by trying to get to that noble gas configuration. But for transition metals, predicting charges is harder, and you can't predict it. So you typically in the name have to give or indicate the actual charge of those transition metals because you can't predict the charge. All right, and what I mean by stock system, we're using Roman numerals here. So the Roman numeral will be equal to that positive charge. And then all other metal cations within that you can predict the charge don't use the stock system. So let's look at some examples here of cations and determine what name we would give them. So this first one, cesium. So if you look at cesium, it's right here on the periodic table. All right, so it's not a transition metal, so you do not need to use the stock system. So this is just a cesium ion. So it's just the name. And I just tack on ion there because it is an ion. This distinguishes it from a neutral cesium atom. Right? Next we have iron 3+. All right, so remember, it's just the name, so iron. But let's see, do we need to use the stock system? So iron is here on the periodic table. It is a transition metal, so we need to indicate the charge to distinguish it from a different charge. So in this case, because I'm telling you it's an iron 3+ ion, in its name we would write iron Roman numeral 3 in parentheses, and it's an ion. All right, next we have sodium plus. Sodium is a main group element, so this would just be sodium ion. Let's keep going. All right. Calcium is an alkaline earth metal. It's also up, you can easily predict the charge. It loses 2 electrons, so calcium 2+. No need to use the stock system here because it's a main group element. So this is just calcium ion. Lithium, the alkali metal, loses 1 electron, so this is just lithium ion. And then copper. Copper is a transition metal. It's right here. it's a transition metal. So we do have to use the stock system to differentiate it from another charge. So this will be copper, and let's indicate the charge. So in this case, it's 2 plus, so this is copper 2 ion, right? So the main focus here is that all cation naming is just the name of the element. And there's just a special step you need to use if that metal is a transition metal. So then you have to use the stock system to indicate that charge. Okay, so let's keep going. And then, yeah, so the only other cation that you're responsible for knowing are one polyatomic cation. So remember, polyatomic just means that there's more than one element in the formula, and the only polyatomic cation that you really need to know is NH4 plus, which is ammonium. Ammonium. And that's the name of the cation that you put into the naming nomenclature convention. All right, and this is actually ammonium ion, ammonium cation. All right, so let's look at now anion naming. It's a little bit different. So cation naming, it was just simply the element name and then maybe the stock system if it's, or the Roman numeral if it was a transition metal. Anion naming is a little bit different. So for anion naming, let's remember that anions are typically nonmetals because nonmetals gain electrons to form negatively charged anions. So just always keep that in mind. So the strategy to name anions, first you want to identify what element it is. And remember that element will typically be a nonmetal. Then you want to replace the ending of the element name, the one that's listed on the periodic table, and replace it with "ide." So let's look at some examples here. So F, which is fluorine. If this was a neutral fluorine atom, we'd call it fluorine. But because it is an anion, F minus, we change that INE ending fluorine, we change it to fluoride. All right, so let's see if you can catch on to the trend here. So sulfur here, this is a sulfur anion. So if this was a neutral sulfur, it's just, a neutral sulfur atom, it'd just be sulfur. So we're going to change that ending because this is an anion. S2 minus, if you look on the periodic table, that's how we predict its charge. You go add 2 additional electrons to get to argon. So that's sulfur 2 minus. The UR ending becomes sulfide. So S2 minus is sulfide. F minus is fluoride. All right, hydrogen. So a neutral hydrogen off of the periodic table, it's just hydrogen. All right. So hydrogen as an anion, we're going to change that ending. Hydrogen, we're going to turn it into an anion, so this becomes hydride. And then finally, nitrogen. A neutral nitrogen atom is just nitrogen. So we're going to change the ending of nitrogen as in a anion will become nitride. So see, in all of these examples, I identified the element first. And then because it's an anion, I changed the ending into "ide." And these are only for monoatomic anions, meaning that it's just one element. Then, so that's naming monoatomic anions. What other anions do we need to know? The polyatomics. So remember, polyatomic just means that there's more than one element in that molecule that's charged. And so for the most part, polyatomic anions are usually a nonmetal plus some oxygens. So we oftentimes call these oxoanions. Oxo meaning contains oxygen. All right, so the steps and strategy for naming polyatomic anions. Well, one, I will always give you, do I have the sheet here? Yeah, here, naming ionic compound sheet here. You will always be given this on an exam, so it has many of the cation and anion naming. You just need to know how to use it. All right, so here with polyatomic anion naming, again, polyatomic anions typically have a nonmetal plus some oxygens. The base root of the name of the polyatomic anion is typically has a root in the nonmetal name. And then when we turn it into a polyatomic anion with oxygens, we typically replace the element ending name with ate, ATE. And so when we put the ate in there, it turns the name into an oxoanion. And then some notes here. If there's an extra oxygen in the formula, typically we put a prefix such as per in front of the name. And then if there's one less oxygen than normal, then typically the ate ending becomes ite. So let's just go through some of these namings. Again, you can refer to that sheet of cations and anions naming to help us through this. So NO3 minus, so we have nitrogen, which is a nonmetal, and we have our oxygens attached to it to make it an overall oxoanion, and because it's negatively charged. This is nitrate, NO3 minus. Nitrate, this is a very, very common polyatomic anion that you will come across. So you will probably just memorize that nitrate is NO3 minus. So CO3, ooh, this is not right. It's CO3 2 minus. Whoops. Sorry about that. So CO3, so we have our nonmetal, which is carbon. This is carbonate anion. And it should be 2 minus. Sorry, there's an error there. The next polyatomic we have here is SO4, 2 minus. All right, so S, that's sulfur. This is sulfate anion. There's our 8 ending. It has an overall 2 minus charge. And then note here where we said if there's one less oxygen than normal, change the ending to ite. So we see we have SO4 2 minus, and then in the next one we have SO3 2 minus. So this oxoanion has one less oxygen, so this is sulfite. So those are some of the polyatomic anions. You can see the whole list in that handout. All right, are we going to practice some naming? Oh, no. Okay, so other polyatomic anions that you should know. Again, polyatomic just means more than one atom within the anion formula. So it's not monoatomic. So some other ones that you should know, OH minus, so that's an oxygen and hydrogen together, overall minus charge. This is hydroxide. CN minus, cyanide. C2H3O2 minus, this is called acetate. HCO3 minus, this is bicarbonate. MnO4 minus. So here it's a little different because manganese is a metal, but overall, when it's combined with 4 oxygens produces an overall negative charge. So it is a anion that we come across. So this is permanganate. And then the last one here, which is also a little bit different because there's chromium is a metal, but it's combined with some oxygens and has an overall -2 charge. This is dichromate. So these are the ones that you need to know and that we will use within this course. All right, are we going to do some examples? Yes. So now let's name some ionic compounds, going through the process of naming them. All right. So let's put our rules together for ionic compounds. You name the cation, then you name the anion. So here, NaF. So sodium is sodium plus off of the periodic table. Fluorine is F minus. There are our cation and anion that make up this ionic compound. So this is sodium, because I just named the cation, and then the anion is fluorine, but it's negative, so it becomes fluoride, sodium fluoride. That's it. Okay, the next one. So nickel and 2 chlorines. So this is where the process of up here where I kind of identified the charges that make up the ionic compound. That's a really useful skill, particularly when naming ionic compounds that have transition metals. Because here we have nickel, and then we have a chlorine, 2 chlorine anions. So chlorine as an anion, remember, is chlorine minus to make chloride. So that means if there's 2 chlorides here, with a -1 charge each, that means nickel must have a charge of 2+ to cancel it out. And this is important when naming, whoops, because nickel is a transition metal. So we need to be able to indicate its charge using the stock system. So the full name for this compound will be nickel 2, because I determined its charge from its chemical formula. And then lastly, it will be chloride, nickel 2 chloride. So in this example, nickel is a transition metal, so we must use the stock system and indicate its charge. So you got to do a little bit of work and inspect its chemical formula to determine what does the charge of nickel have to be to make that compound overall neutral. Okay, let's keep going. So CsNO3, so cesium on our periodic table is right here. It's in the same group as lithium, so this is cesium plus. Nitrate is one of our polyatomics, so it's NO3 minus. Cesium is not a transition metal, so we don't have to do stock system. So simply, this is cesium, named the cation, and now name the anion, that's nitrate, cesium nitrate. Let's keep going. Calcium carbonate. So calcium is Ca2+, carbonate is CO3 2-. So name cation, anion. This is calcium carbonate. Calcium is a main group element. It's not transition metal, no stock system. Carbonate. Okay, let's keep going. Okay. NH4OH. So identify the cation. In this case, it's NH4 plus. And then OH is another polyatomic. In this case, it's an anion. So it's OH minus. So to name this, you just name the cation, ammonium, and then name the anion, ammonium hydroxide. Okay. All right, let's keep going. Okay, so sodium, and then one of our polyatomics is sulfate. Sodium is a main group element, so this is just sodium sulfate. And see how I am not indicating the number of sodium atoms here? Because you never do that with ionic compounds. You only ever use the stock system to indicate charge in a transition metal. All right, next, potassium, potassium. PO3 is a polyatomic. This is phosphate. Potassium phosphate. All right. Ooh, iron and a sulfur. I know that iron is a transition metal, so we will have to use the stock system here. So sulfur, so the steps to do this one, because we do have a transition metal, I know it will be iron, because that's the cation, but I need to know the charge so I can do the stock system. So sulfur is here on the periodic table. It's 2 spaces away from argon, so sulfur will gain 2 electrons. So typically as an anion, sulfur is 2-. So since there's only one sulfur, that means in order for this to be neutral, iron must be iron 2+. So that means when we name this, it is iron 2, name the anion with the appropriate ending, so it's just sulfide. Iron 2 sulfide. All right, next one. Okay, so copper, also a transition metal. Both of these are transition metals, the next two. All right, so again, we're going to have to figure out what is the charge of copper. So we see the anion polyatomic here, it's hydroxide. We know that hydroxide is a -2, or sorry, -1 charge, but there's 2 of them. So overall, this is a -2 charge since there's 2 hydroxides. So if there's an overall -2, that means copper, to balance the anion charge, copper cation must be 2+ in order to cancel it out. So to name this, it will be copper, it's the stock system, copper 2 hydroxide. And so this kind of contrasts with the next one here. So again, we have copper and hydroxide, but it's a little bit different. Hydroxide, remember, only has a -1 charge, so that means copper in this chemical formula only has a charge of +1 in order to be net neutral. So to name this, it will be copper 1 hydroxide. So this is how we distinguish the charges of transition metals. So in this case, the charge on copper is 2+, so we need to have 2 hydroxides to balance it. So that's how we indicate it in its name, copper 2 hydroxide. And then in the second example here, we only have 1 hydroxide associated in this formula unit. So copper needs to only have a charge of +1, so we call it copper 1 hydroxide. Okay, so I think where a lot of students get caught up are with the transition metals. So always identify in your metal cation, is there a transition metal present? Is that metal a transition metal, or is it a main group element? If it's main group, then you don't need to use the stock system. But if it is transition metal, you need to use the stock system, and oftentimes have to inspect the chemical formula in order to determine what those charges are. Okay, so now let's kind of work backwards now and think about how can we go from a name to a chemical formula. And a lot of this is just knowing knowing how to predict charges of cations and anions, and identifying what polyatomics are on the list that we have and what charges those are, and then combine them in such a way to form a chemical formula that is neutral. So in this first example, we have iron 2 hydroxide. So we want to turn this into a formula. So my first step here is to identify, okay, what's the charge of the cation? What's the charge of the anion? I like the stock system because it straight up just tells you the charge. So iron, has a chemical system symbol of Fe, and it tells us it's 2+. So this is iron 2+. And then hydroxide. If you look at the polyatomics list, hydroxide is OH-. So now we need to think, okay, how can we combine these two to make it neutral? So in my mind, I want 2 hydroxides in order to cancel out the positive 2 charge to make it overall net charge 0. So the chemical formula for this compound will be iron hydroxide, 2 of them. All right, next, lithium nitrate. So lithium is our metal. It's just a main group element, so we just look at where that is. So lithium's right here. So lithium as a cation is lithium plus, because it's going to tend to just lose 1 electron. So lithium plus. Nitrate is one of our polyatomics. That is NO3-. So think about how the charges need to combine to be neutral. So in this case, it's just a 1-to-1. So the chemical formula here will just be lithium nitrate. Nice and neutral. Okay, next. Potassium permanganate. So again, potassium on the periodic table right here, same group as lithium. So it's also going to just lose 1 electron to produce potassium plus cation. Permanganate, that's one of our polyatomics, so MnO4-. So look at the charges, +1, -1, just a 1-to-1 ratio, so this compound is KMnO4. That's it. Let's keep going. Sodium carbonate. Sodium, where's that on the periodic table here? 11. All right, so sodium, same group as lithium and potassium. So sodium will form the cation Na+. Carbonate is CO3 2-, according to our handout. And so let's think about how those charges interact. So we have a 2- and just a +1. So in my mind, I want 2 sodiums to cancel out that -2 charge, because 2 sodiums will produce a total +2 charge that will cancel out with the -2 charge. So to write that as a chemical formula, Na, but we want 2 of them, Na2CO3. So that's sodium carbonate. How many more? Okay, just 2 more. All right. So titanium 4 oxide. Again, I love transition metals because naming them this way, because it just tells you the charge. So titanium has that element symbol. The stock system is telling me it's a +4 charge. Perfect. Oxide. So oxygen is here on the periodic table. It's 2 electrons away from neon, so it's going to gain 2 electrons. So oxide is oxygen 2 minus. Okay, so let's think about how does +4 and -2 combine. So in my mind, I think, okay, I need 2 oxygen anions to cancel out that charge. So titanium 4 oxide will have the formula TiO2, because 2 minuses will give me an overall 4 minus and cancel out with that 4 plus. Okay, lastly, magnesium chloride. Where's magnesium on the periodic table? Here, right? So it's going to lose 2 electrons to produce magnesium 2 plus. Chloride, here on the periodic table, it's going to gain 1 electron to make Cl minus. So if you combine that in such a way to be neutral, you need 2 chlorines or chlorides to give you MgCl2. So that's how to go from a name to the actual formula unit or chemical formula for that ionic compound. And see my steps here. I broke it down into cation and anion, identified the charges. If you don't identify the charges, then you don't know the ratio and the subscripts needed to produce an overall neutral compound. So the steps I did here, where I identified the charges, that's imperative in naming of ionic compounds in this way, going from a name to a chemical formula. All right, so that's it for chemical naming for ionic compounds. So again, these 2 tables will always be given, because I don't like, in this kind of class structure, let's forget about memorizing things. You will always be given these exact 2 sheets on an exam. So just know where our common polyatomics are. Here's acetate, carbonate, sulfate, nitrate. Some of the other monoatomics are there too, but you should just be able to predict that off of the periodic table. Yeah, so that's all there for you. So that's ionic compound naming. Stay tuned, and we will talk about molecular compounds.